Okay, good morning. We're going to take a look at section 6.2 today, which involves solving quadratic equations by factoring. One of the skills that we learned back in chapter 5 was how to factor quadratics, and that skill is going to come back into play here when we try to find the solutions to a quadratic equation. So that's, for starters, what we're going to be taking a look at is solving these quadratics. And secondly, we're going to take a look at how to solve real-world problems that deal with a quadratic model and then finding its roots by factoring. So what I'd like you to do is I'd like you to picture a quadratic that does not have any x-intercepts. What does the quadratic look like? What does a quadratic look like with one x-intercept? What about one with two x-intercepts? So what you should be visualizing, a quadratic that doesn't have any x-intercepts, would be a quadratic that opens upwards and its vertex is above the x-axis, or one that opens downwards and its vertex is below the x-axis. So these will have no x-intercepts for either the first one or the second one. Okay, if you want one x-intercept, of course your vertex is going to be on the x-axis opening upwards, or on the x-axis opening downwards. And the third scenario is two x-intercepts. So you would have your vertex below the x-axis opening upwards, or your vertex above the x-axis and your quadratic opening downwards. Now, coming up with equations for these is just a matter of matching where your vertex is and your value of a. For example, these middle ones here, there should be no shift up or down. So you could say y is equal to x minus 3 all squared for the first one over here. And then the second one, y is equal to negative, let's say x plus 4 all squared, because I've moved it 4 units to the right, to the left. This is not to scale, of course. Keep that in mind. I'm just after a general idea of what it looks like. Whereas these ones here, this first one, you could say y is equal to, we want it opening upwards, so any value of a that's positive, so x minus 3 squared minus 4, because we want its vertex to be at 3, negative 4. For this one over here, we could say y is equal to, we want it opening downwards, so our a value will set to maybe negative 3, and we can have our vertex be 2 and 5, let's say. So x minus 2 all squared plus 5, that'll do it for that one. So hopefully that makes sense to you. You would obviously have gotten different ones. These ones over here, which I didn't do equations for, we're after an equation where the a value is positive for this one. So maybe 2x minus 3 all squared, because we're going to put the vertex at 3 and let's say 1. So plus 1. And notice your a value is positive here. So the quadratic is opening upwards with vertex 3 and 1. So let's just pause there for a moment. Okay, so let's take a look at some theory first. So how is a quadratic equation different than a linear equation? Well, a quadratic equation in one variable has a degree of 2, and it's of the form ax squared plus bx plus c equals 0. Now, both a, b, and c can be any real number, and of course, a cannot be 0. Because if a is 0, then this term zeroes out if a is 0. And then that would simply be a linear equation. So here are some examples of some quadratic equations. 2x squared plus 3x plus 1 equals 0. Negative 3x squared minus 6x equals 0. And x squared minus 4 is equal to 0. You'll notice in the first one, all three terms are there. The quadratic term, the linear term, and the constant term. In the second term, the quadratic term and the linear term are there. And in the third term, just the quadratic and the constant term are there. So those are your three possibilities. You're never going to have the possibility where the quadratic term is not there, because then it is a linear equation. So solving a quadratic equation of this form means finding x values that make the equation true. In addition, solving a quadratic equation is equivalent to determining the x-intercepts of the quadratic relation y equals ax squared plus bx plus c. When you let y equal 0, you're finding the x-intercepts. So one of the things we saw in our warm-up here was that not all quadratic relations have x-intercepts. So it makes sense that not all quadratic equations can be solved. In other words, there may not be a solution, so no solution to all quadratic equations. We can either solve by factoring, or we can use something called the quadratic formula, which we're going to see later in this chapter. If the quadratic ax squared plus bx plus c can be factored, then its corresponding quadratic relations, x-intercepts, are rational numbers. So they're either integers or signed fractions. If the quadratic equation cannot be factored, then its x-intercepts are irrational numbers, or they don't exist at all. This is something that we're going to be using the quadratic formula to decipher once we know that it cannot be factored. So here's the general theory behind finding roots or x-intercepts by factoring. If the product of two numbers is 0, then either one or both of the numbers are 0. In other words, if I say a times b equals 0, then it must be true that either a is 0 or b is 0, or both. Usually not both for the types of problems we deal with. Problems we deal with, it's either the first one is 0 or the second one is 0. So to solve a quadratic equation by factoring, first we write the quadratic so that it's in the form ax squared plus bx plus c equals 0. Then we factor the left side. So we make sure that we factor any GCFs out, including the negative sign from the quadratic term. Then we set each of the linear binomials to 0. In some cases, an equation may have linear, quadratic, and constant terms on both sides, such as this one here. So 3x squared minus 5x plus 2 is equal to 5x minus x squared plus 1. You would collect all the terms on one side and set the other to 0. So let's take a look at these first two questions here where we have to solve for x. So we have negative 2 times x minus 4 times x plus 10 is equal to 0. It follows that either this first binomial is 0 or the second binomial is 0. And I love drawing hearts around this because it drives my students crazy when I do that. So x has to be 4 or x has to be negative 10. If you go back and substitute that into the original equation, if you put 4 into this binomial, it'll be 0, and the entire left side will be 0. Or if you put negative 10 into the second binomial, it will be 0. So let's take a look at this second one here, which is going to be a bit more work. So 2x minus 1 times 3x plus 2 is equal to 0. So the first binomial is 0, or the second binomial is 0. I don't have enough space there to put a heart, so I'm sorry to disappoint. So we'll have 2x is equal to 1, or x is equal to 1/2. As you get better with these, you'll be expected to skip this step entirely and be able to jump right to x equals 1/2 from 2x minus 1 equals 0. In fact, this one here is negative 2/3, and I'll take you there one step at a time. So 3x is equal to negative 2, and then of course divide both sides by 3, and we're done with that one. In problem 2, you'll notice that none of these are factored. So let's start with the first one. We've got x squared is equal to negative 2x plus 8. We'll bring all the terms to the left side. So x squared plus 2x minus 8 is equal to 0. And we want a product of negative 8 and a sum of 2. And if you've guessed x plus 4, x minus 2, you've guessed correctly. So my roots are going to be x plus 4 is equal to 0, or x minus 2 is equal to 0, which means x has to be negative 4, or x needs to be 2. If you go back and substitute that into the original equation, negative 4 squared gives me 16 on the left, and negative 2 times negative 4 gives me 8, plus 8 gives me 16. So that makes the left side equal to the right side. And the same thing happens when you substitute x equals 2. X equals 2, on the left you would get 4, and on the right you would get negative 4 plus 8, which is also 4. So when we get to b, 30 is equal to 2x squared minus 4x. I like to keep the a terms positive when you can. So I'm going to bring all the terms to the right. So 0 is equal to 2x squared minus 4x minus 30 is equal to 0. This definitely has a GCF of 2. So here we go. And we want a product of negative 15 and a sum of negative 2. So that, of course, is x minus 5 and x plus 3. And so that means that x minus 5 must be 0, or x plus 3 has to be equal to 0. So let's take a look at C. We'll scribble C over here. Negative x minus 3 is equal to negative 10x squared. Again, I like to keep the a term positive, so we'll bring that term over to the left. So minus 3 is equal to 0. There is no GCF for this one. So then I do need to break out my method of dealing with these complex trinomials that we learned in the previous chapter. So again, we want two terms that multiply to 3. Well, 3 and 1 is really the only way we're going to be able to do that. And we'll try 5 and 2 over here. So 5x and 2x. In this direction here, I get 5x times 1 is 5x and 6x. That's 11, which is not negative 1. But one of these two numbers needs to be negative, either the 3 or the 1. The 3 needs to be negative because we'll get negative 6x plus 5x gives us negative x. So our binomials are 5x minus 3 and 2x plus 1 is equal to 0. So that means that x has to be 3/5 or x is equal to negative 1/2. So take a moment there to do the steps that I've skipped, and maybe I'll show you. So 5x minus 3 is equal to 0. Bring the 3 over, and then divide by 5. So that's over here what's happened in between. Eventually, you're going to be expected to be able to skip that. And question D, negative 6x squared minus 17x is equal to negative 3. It's too much effort to bring all the terms to the left to keep a positive, but that's okay. We'll just bring that lonely 3 over, make it positive. Now, always GCF the negative 1 in front, and the negative in front of the x squared. That's really important. So we're going to factor out a negative because there isn't anything else that's common. We get 6x squared plus 17x minus 3 is equal to 0. And again, using your method that we learned in chapter 5 to factor this. 17x, 6x and 3x ought to do it. And actually, sorry, 2x, because 6 times 2 is, oh, good golly. Let's try that completely over again. 3x and 2x. Let's see if that works. And we'll try 3 and 1. 3 times 1 and then 6. One of these has got to be negative. That's not going to get me to 17. If I flip the 3 and 1 the other way, so 1 and 3, that still doesn't get me to 17. So this choice here of 3x and 2x is probably not the best way to go to choose those. Let's try 6x, or simply x and 6x. We do get 6x squared. When we multiply across and add, we get x and then 6. That's not really close to positive 17. But if we flip these back the other way, if we flip these back to 3 and 1, this way we get 18x, here we get positive x. We've got it, because remember, one of these needs to be negative because we need a product of negative 3 here. So my factors are going to be x plus 3 and 6x minus 1 equals 0. So we get x plus 3 is equal to 0, which we know is just negative 3, or 6x minus 1 is equal to 0, so 6x is equal to 1. x is equal to 1/6. Eventually, of course, I want you to recognize that you need to be able to get there in one step. Before we go too far with any other questions, I want to point out something that is really, really important, and it is very, very subtle, okay? It's not altogether obvious, okay? Each of these quadratics, you're finding what makes the left side equal the right side. If you look at just this right here, this left side, this is a quadratic that opens downwards, right? Hopefully you agree with me on that. And I'm going to guess that its vertex is somewhere over here. What we actually found, maybe my drawing needs to be adjusted slightly. What we found here is that this value of -3 here occurs here when x is equal to 1/6, and over here when x is -3. And this y coordinate came from this. Graphically, a little beyond what we're dealing with in this course, but question A, you've got this quadratic equals to this linear. You know what we just found there was, we found the point of intersection of those two functions. In grade 11, you're going to learn the term function to describe special relations. These are special relations. Here is your quadratic, which is your left side, and here is your linear, which is your right side. We just found those 2 points of intersection by doing what we did in question A. Okay. Let's pop down to problem 2, because I think I did all of those, A, B, C, D. Yep, we're good. So let's take a look at problem 2, and we'll solve it using this factoring method to solve these quadratics. So a water balloon is shot in the air from a catapult such that its height in meters is given by this equation. So first thing we should recognize, and you should visualize this in your mind, is that this is a quadratic opening downwards. I'm not quite sure what the starting height is, but well, I know what it is, but it's going to look something like this. So this is what you should be thinking, that it looks like that, or even it looks like this with the starting point at 0. Here it's not at 0. So it's one of these two scenarios. So let's see what we can do with this. So we want to know, when does the ball hit the ground? Well, that happens when h is 0. So we know that 0 is equal to -5t squared plus 55t. And this is GCF factoring here because we only have 2 terms. We're going to factor out a -5t, and we're left with t minus 11. So it hits the ground, well, not it, the ball, or the balloon, pardon me, the water balloon hits the ground at t equals 0 and t equals 11. Now that's a great thing to know because we now know 3 things. We know that we have an x-intercept there, another x-intercept there, and, wait for it, we know that the axis of symmetry has to be 5.5. Think about how I got the axis of symmetry. I added the roots and I divided by 2. So nothing spectacular there. And then to find this y coordinate, you would sub it into the original equation. Well, let's take a look at the next problem here, problem B. When is the balloon's height exactly 50 meters? So we have to solve this quadratic equation. So -5t squared plus 55t. We'll bring all the terms to the left just because, actually we'll bring everything to the right just so that I force you to get into the habit of factoring out that negative out of the quadratic term. So -5 definitely factors out, so t squared minus 11t plus 10, and this factors to t minus 10 and t minus 1 because we're looking for a quadratic whose binomials where we have a product of 10 and a sum of negative 11, and that only occurs at negative 10 and negative 1. So this is 0 when t is equal to 10 or t is equal to 1. So that's when the height is 50 meters. So if we take a look at what I have over here in my graph, there's 1. This is not drawn to scale. Okay? This is just a rough sketch. You'll notice that they're equidistant from the axis of symmetry. So that's always going to happen, that you're going to have partner points that are equidistant from the axis of symmetry. One of the things that we can do in this problem is we can talk about the domain. We know that the domain is x is an element of the reals, and it's between, I believe, 0 and 11. We, however, cannot talk about the range because we don't know the maximum height. We know the minimum height is 0. That's where it hits the ground. You're going to use h here, not y. Let's fix that up. H is an element of the reals, but we don't know this upper bound. So how would we find that upper bound? Well, we know that the axis of symmetry is x equals 5.5. We sub x equals 5.5 into h is equal to negative 5. That's not x, that should be t. Oh, wait for it. What a scandal. Yes, you're right. I set that up on purpose. I wanted to be able to say that. I know it's been over 6 weeks since or 5 weeks since we've seen each other, and you're probably missing that silliness that I often engage in class. So plus 55t. So let's fill that in. So that's going to be negative 5 times 5.5 squared plus 55 times 5.5. And I'll give you a chance to work that out. I'll work it out as well. Hopefully I won't make any errors because I don't like having to do a video twice. 55 times 5.5. Yeah, that's not right. 5 times. When you pop that on your calculator, you should get 151.25. So we'll just slide that in there, 151.25. And just so you see how everything fits in, I now know that h is equal to negative 5 t minus 5.5 all squared plus 151.25. Did you see how I put together the whole equation based on what I've done with the work that I've done so far? That negative 5 in front came from the original question, which takes us to the third and final problem here, where we have a word problem. And this is quite a common occurrence, this type of problem. A particular manufacturer sells widgets direct to customers. I don't know what a widget is. It doesn't really matter what it is. It currently sells 10 widgets per hour when the price is $50 per widget. So when the price is $50, they can sell 10 widgets per hour. Based on market research, it's estimated that sales will increase by 2 widgets per hour for every $1 drop in price. So what price should the manufacturer sell the widgets in order to ensure a revenue of $1,200 per hour? Now, one of the things I want you to recognize is this is a completely different problem than what you would have done in section 6.1. One of the major reasons why we always cover section 6.1 with chapter 4, we want you to at least master finding the maximum or the minimum by completing the square negative b over 2a before you start mixing multiple types of problems in the same unit, which is why we did 6.1 separately. But we start pretty much the same way. We start by saying, let x represent the number of $1 decreases in price. And my revenue is going to be our price times our quantity sold. The thing in this problem is quite often students will focus on this every hour. It's completely irrelevant. It's just a matter of making the problem sound really official. So our price, we're going to come up with a binomial. When the price is $50, we're decreasing by $1, so 1x. X is the number of decreases in price. And then, of course, our quantity increases by 2, so 10 plus 2x. And let's just test this. When there are no price increases, your price would be 50 and your quantity would be 10 because x equals 0. When there's one price decrease, your price would be 49 and you would sell 12. So that seems about right to me. So let's expand this. We get 500 plus 100x minus 10x minus 2x squared. We'll collect the like terms, so negative 2x squared plus 90x plus 500. And so this is the revenue. Let's just call it R for short. Now, in the previous questions, we were looking for the vertex. What's the maximum revenue and when does it occur? Here we're looking for when is the revenue $1,200. So essentially we have to solve this quadratic equation. So we want to know when is R 1200. We'll bring everything, the 1200 over to the left, pardon me, to the right. So negative 2x squared plus 90x, I think minus 700. And let's see if we can factor that. And we should be able to GCF a negative 2. And we're left with x squared minus 45x plus 350. And at this point, to be honest, sometimes students really struggle with finding a product of 350 and a sum of negative 45. And that's why, quite honestly, we have this quadratic formula, which we'll learn later. But this one is quite obvious that the numbers are 35 and 10, because 35 times 10 is 350, and they add to 45. If we make them both negative, that gives us what we want. So our binomials are going to be x minus 35 and x minus 10. So this, of course, gives us 35 or x equals 10. Now keep in mind, we wanted to know what price. Remember, the price, this is not the price. The price is 50 minus x. So it's going to be 50 minus 35 or 15, or the price is going to be 50 minus 10 or 40. Now our quantity, remember that the quantity was 10 plus 2x. So 10 plus 2x. And for this first case over here, x is 35. So we get 10 plus 70 or 80. And for the second one, the quantity was 50 minus, pardon me, 10 plus 2x. And of course here we're talking about x equals 10 for this one, and for this one down here, I believe we get 30. If we double check our revenue, revenue is price times quantity, do we get 1200? I do know for this one we do right away. 40 times 30 is 1200, but is 80 times 15 1200? In fact, it is, because 80 times 10 is 800, and then 5 times 80 is 400. Add them, and that's 1200. So hopefully that helps. I believe that's it for section 6.2. Good luck with everything, guys. Take care and stay well.